All right, so let's get started. Welcome to week 4 of CS50. If you guys open up a web browser and open up pset 3, Scramble with CS50, we're going to start going through the section of questions there. Just like last week, we'll be working in CS50 spaces. So if you'd also pull that up as well. And if you go ahead and visit this link that I've got up here at the top. All right. So to get started, we've got our little hi program here. Nothing crazy. So one of the first things I want to do with you guys today is go over a few solutions to problem set 1 that are kind of example solutions, just so you can get a feel for what kinds of code staff is writing, what kinds of code other students are writing, and just have you take a look at it, because I know it's weird when you submit a solution to a problem set and get comments on your own version, but sometimes it's helpful to see how other people did it, especially ones that are nice looking. So for the most part, I was really impressed with the solutions that you guys produced. So I haven't yet started looking at your problem set 2s, but if they're anything like the first, it means nothing but good things. So if you look at my revisions, let's start all the way down at revision 1. And we're going to take a quick look at a Mario solution. So if you pull this up, these programs that we're going to present are correct. So there weren't correctness issues with these problems, but rather we want to talk a little bit about the different design issues that were being used here. So one of the things that was interesting about this solution is that it used this new construct called a pound define, sometimes also referred to as a hash define. Let me zoom in on it here. So a pound define allows you to give names to these numbers in your program. So in this case, the maximum height of a pyramid in Mario was 23. And rather than putting 23 in my code, and we would refer to that as hard coding 23, instead, this gives the name max height to that number. So that down here in my do while loop, you can actually refer to max height instead of putting the number 23 in.
What is the advantage of doing that?
Yeah, that's a great question. So one is just readability. So an advantage of using this pound define is readability. You know, when I'm reading this code, I can see what's going on. I can see in this condition here that we're testing for the height being less than 0, which we could have also defined to be a minimum height or a min height. The other advantage is that I can then read the rest of the line to see that we're also checking to make sure that height is not greater than the max height, because we're going to continue while the height is greater than the max height. The other advantage is, if I zoom out a little bit here, if I run this program, and I run it, say, with 23 right now, it'll print out all 23 rows, just like that. But say I wanted to change the max height, and now I wanted to limit the maximum height of pyramids to be only, say, whoa, man, that was funky. Pound include standard io.h, pound define max height, and let's say we wanted to set it equal to 10. So now at this point, all I had to do is change it in this one location. I can recompile the code, and now if I try and type in 12, it'll prompt me again. So in this case, we're only using max height once. It's not that big of a hassle to go and change it in the while loop if you need to. But in programs where you're referencing the same sort of magic number over and over again, this pound define mechanism is really handy, because you just change it one time at the top of the file is typically where you put them, and the change percolates through the rest of the file. So other things I wanted to note in this assignment that I thought looked really nice. One was just the naming of the variables. You see here that we've got integer variables called row and called height, excuse me, spaces, hashes. It helps make the code a little more readable, makes it kind of a little more understandable what's actually going on. You know, this is in contrast to using, say, random letters or just gobbledygook altogether. A final thing I'll point out is that in for loops, often these iterator variables, these counters that you use in your for loops, it's standard and just conventional to start them with either I and then j and then k and going on from there if you need more variables. And this is just a convention. There are lots of conventions. It kind of depends on the programming language you're using. But in C, we typically start with I. So it doesn't make sense to use, say, A or B, depending on the situation. All right, so that's it for this one. If we now pull up revision 2, see another Mario. And this one is similar to the other one that we just saw, but it does something kind of cool. If we look at this section right here inside the inner for loop, they're using some crazy looking syntax here, right in this line. So this is called a ternary operator. It is an if-else statement condensed into one line. So the condition is this part within parentheses. It's equivalent to saying if j is less than height minus I minus 1, and then what the contents of that if block would be are this space, and then the contents of what the else would be are this hash. So it's essentially assigning a space to this variable. It's putting a space in the contents of the block variable if this condition is met. And if the condition is not met, then the block variable gets this hash. And then, of course, instead of building up an entire string and printing everything out at the end, this solution prints it out one character at a time. Pretty cool. All right. Now there are a couple things to look at. We'll move on to greedy. So now if we look at greedy, this first solution uses these pound defines quite a bit. So we've got one constant defined for each of the different numbers in this program. We've got one for cents per dollar, one for quarters, dimes, nickels, and pennies. And now if we scroll down and read the code, we can see standard do while loop printing everything out. One of the kind of the crux of this problem was realizing that you needed to convert the float that you read in from the user to an integer to accurately do the math. And this is because with floating point numbers, like we talked about in lecture briefly, it's not possible to accurately represent every single value on the number line because there are infinitely many values between 3 and, say, 3.1 even. You can have 3.01 and 3.001 and 3.0001, and you can keep going. So it turns out whenever you're working with money, you often want to convert it into integer format so that you're not losing pennies and that kind of stuff. So doing that and rounding was key. This solution used a perfectly straightforward, great algorithm, which just decremented the number of cents remaining, first by quarters, then by dimes, then by nickels, then by pennies, and adding to the number of coins each time. Another solution that we'll see as I zoom out and go to revision 4 had a very similar beginning, but instead used div and mod right over here to calculate the number of cents. So this said that the number of quarters is equal to the number of cents divided by 25. And the reason this works is because we're doing integer division, so it's discarding any remainder.
Do we have to comment this much?
It really depends. So
You're commenting more than coding
Yeah, and so there are a bunch of varying philosophies on this. My personal philosophy is that your code is really the truth, right? Like your code is what's actually executing on the computer, and so your code should be as readable as possible to not necessitate as many comments. That said, when you are doing things that are kind of tricky mathematically or algorithmically, it's good to comment those so that you can add an extra dimension, an extra layer to whoever is reading your code. In these solutions, often they're commented more heavily just because we want to be able to distribute them and have people pick them up and read them pretty easily. But definitely, you know, this is, I would agree that this is heavy. Cool.
When in doubt, go heavier.
When in doubt, go heavier. I mean, so some people will sometimes say, you know, return 0 or something like that. Like, I think that's kind of a ridiculous comment, right? Like, clearly that's what's happening. I don't need English to tell me that. Sometimes people will write stuff like, okay, thanks, bye. That's kind of cute, but also not, you know, that's not making the difference between getting commenting points or not. You know, like those kinds of comments are just, you know, haha. Cool. So at this point, let's start working on problem set 3's section of questions. So if you guys pull this up again. As with last week, we're not going to watch the shorts in this section. We'll let you guys do that on your own time and talk about the questions. But now in this section, we're going to spend a little more time talking about less of just the coding basics like we did last week. And instead, we're going to focus more on a little bit more of the theory. So talking about binary search and then sorting. So from those of you who have been following along with the lecture, can somebody give me a recap of what the difference is between binary search and linear search? What's going on? Sure.
Linear search searches through every element in the sorted list one by one by one by one by one. And binary search divides the list into two groups, checks if the key value that you're searching for is greater than or less than the midpoint value that you just found.
Mm-hmm.
And if it's less than, it goes with the lower list and then divides that again, does the same function all the way down until it finds the midpoint to be equal to the value itself.
Right. So why do we care? Why do we talk about binary search versus linear search? Yeah.
Well, binary is a lot faster.
Yeah.
So if you double the size of the problem, it takes one more step rather than twice as many.
Exactly. That's a great answer. So linear search is very much, you know, checking one element at a time. And as we saw on the very first day of lecture when David went through his phone book example and ripped out one page of the phone book at a time and kept doing that over and over and over again, it was going to take him a really long time to find anybody in the phone book, unless, of course, he was looking for somebody at the very beginning of the alphabet. With binary search, you can go a lot faster. And it's not just twice as fast or 3 times as fast or 4 times as fast, but the problem gets smaller and smaller and smaller much faster. So to illustrate this, we'll start talking about what's going on when we write binary search. So the problem at hand is that if I have an array of numbers, say 1, 2, 3, 5, 7, 23, 45, 78, 1, 2, 3, 2, 3, 2, 3, and then 9 with a ton of zeros after it. We want to be able to figure out really quickly what is in this array of numbers. So I know this seems a little silly and a little contrived because right now it is. We have an array that doesn't have very many elements in it. And if I asked one of you to figure out whether or not 23 is in the array, you can do that pretty quickly just by glancing at this and telling me yes or no. So the analog to consider is, imagine if this were, say, an Excel spreadsheet with 10,000 rows, 20,000 rows. Of course, you can do the Command F or the Control F and look something up. You can also use like the filters and the search stuff. But if you just had to look through that file line by line by line, it would take you a long time to find it. It's kind of like in the phone book example too, where nobody looks through a phone book one page at a time. Typically, they do kind of open it to the middle, or in the case of a lot of phone books and dictionaries, where you actually have it keyed on the first letter. You flip to that first letter and open and start going through there. So, remind me of your name again? Sam. So, like Sam said, that linear search process is going to be really slow. And instead with binary search, the way this works is that every time we go through an iteration of our searching algorithm, we're going to divide the list in half, essentially, into two smaller lists. And then on the next iteration of the loop, we'll divide it again into other smaller lists. And so as you can see, the problem keeps getting smaller and smaller because we keep discarding half of the list every single time. So how does this discard work? Well, just as a reminder, what we're going to do, if we were a computer and we were, say, searching for the number 5 in this list, is that we would pick a number in the middle. So in the middle of this list, because there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers, we'd pick the number either at the 4th position or at the 5th position. And we'd call that the middle of our list. So pick number in middle. Then, just like Sam said, we'll test to see if that number is equal to the number that we want to get, to our desired number. If it's equal, then we found it. We win. If it's not equal, then there are a couple of cases. The two cases are either, well, the number has to be greater than the number we're looking at, or it's less than. So if it's greater, we move to the right. And if it's less, we move to the left. And then we repeat the whole process again on either the right half or the left half of the list. So the first problem in today's section is to figure out how we can actually start to express this in C code. We've got the pseudocode here. What we'll start doing is I'll pull up a brand new space, save this revision so that we have these notes for later. We'll delete all this. And then I'm going to copy and paste from the problem set this information into our spaces. Hopefully this doesn't break. Perfect. So if you guys all do that, copy and paste this code into your new space, into a blank one. Let's try Daniel. If you compile and run this program, does it work?
No.
Okay, what's it saying?
It says the control reaches end of non-void function.
Yeah, so let me try running it. Have you guys seen this before? You know what this means? Okay, so let's dissect this a little bit. It's saying at file.c on line 9, column 1, we have an error, just like you said. And it says that it's stemming from the error warning and the return type warning. So it looks like something's going on with a return type, which makes sense. We've got a non-void function, which means that we've got a function that doesn't return void. So a void function is one that looks like this, void foo. And it's void because the return type is void, which means that if we had something in here like return 1, we'd get a compiler error for this. However, we have a non-void function. Our non-void function in this case is our search function because it has a return type of bool. So when it's saying that the control reaches the end of a non-void function, it's because search doesn't have a return statement. It's not returning anything of type bool. So we can fix that. And what do you guys think search should return just by default? What should be the default return value of search? Because that's what we can put at the end. Charlotte, do you have any?
True or false?
True or false? Which one?
False. I don't know.
False. Let's try it. Why would you say return false? That's great intuition.
I don't know.
OK. Yeah. So we're going to return false in this case because this will be kind of our default. If for some reason the list is empty or the needle that we're looking for doesn't exist, then at the very end, if we don't return true earlier in this function, we always know that this function will just say, nope, it's not in the array. It's not in the haystack. So now if we compile and run it, let me save this so you can pull it up. Now if we compile and run our program, it builds. We get our little prompt. If I hit 4, uh-oh. Didn't print out anything. Looks like everything ended OK. So we got to fill this in. All right. So we talked about the algorithm in pseudocode just a little bit ago. Let me see. We'll save this, and I'll pull that algorithm back up again. Was it this guy? Nope. There it is. OK. So how do we do this? What would be a good strategy for starting off this code? We have to pick a number in the middle. How do we pick a number in the middle of an array? Any suggestions? Sterlen divided by 2. That's a great one. So Sterlen works with special kinds of arrays. What kinds of arrays? String arrays. Yeah, character arrays. So it's that same sort of concept that we want to apply, but we can't use Sterlen because we don't have an array of characters. We have an array of ints. But what does Sterlen get for us? You know what it gets for us? Exactly. Yeah, it gets us the length. So Sterlen gets the length of the array for us. So how do we get that in our binary search program? How would you get the length of an array?
Sterling?
So you can get the length of a properly formatted C string array with Sterlen. The problem, though, is that we don't have a string array. If we look back at this code, we have this integer array. So how do we know how long it is?
Is there an equivalent one for like INTL
Yeah.
or something? Okay.
So it turns out that there actually isn't, and so in a way this is one of those things that's just good to know about C, that there is no way to get the length of an array if all I give you is the array. The reason it works with strings, the reason Sterlen works, is because if a string is properly formatted, it will have that special \0 character at the very end. So if you can also imagine if you have an improperly formatted string and there's no \0 character there, then the whole thing doesn't work.
Can you add a \0?
So we could, in this case, we could add some sort of \0 or some sort of like signifying character and then use that. But that's not quite going to work because the \0 is for a char type. And here we've got ints. The other thing is if we were to, say, use a special value like -1 to mark the end of an array, then we could never store a -1 in our integer arrays. Right? We'd be stuck. So it turns out that the only way to get the length of an array in C is to actually remember it when you set it up and then pass it around with the array. So that whenever I have a function that's going to do some work on an array of integers or floats or doubles or what have you, I also need to give the function the array's length. And that's exactly what we've done here in the search function. So if you look, what we've done when we pass in our array here, we also pass in the length, the size. It just happens that we have called this variable here, this parameter or argument. This is called a function's argument list or parameter list, and these are also called arguments or parameters. People use different terms at different times. I sometimes interchange them myself. It just so happens that this variable here is named similarly to this #define up here, right? But they're not the same thing. The capitalization does matter. So if you look what happens here, we declare our int array, which we've called numbers. We've given it our size, which corresponds to our #define up at the top. It's going to be 8. And then when we then call our search function down below, we pass in the number we want to search for, which we've prompted and gotten from the user. We pass in the array as numbers. And then we also have to pass in the size of the array. And then the value of size, 8, gets stored or passed to this integer variable called size. So we have the size of the array. So now if we go back to what we were talking about earlier, I think Missy brought up the point that what we needed to do is get the length of the array and divide it by 2. And that'll give us the midpoint. So let's see, can I have somebody write this and save it in their space? Well, Layla, can I have you write this and write the first line where you take the length of the array and get the midpoint and store it in a new variable? Give you a couple seconds and then are you ready? Sure. Could I have you calculate the midpoint of the haystack array inside the search function using the length of the haystack array, which is this size variable? Nothing tricky here, just
like size and array by 2?
Yep. And
just
save it.
like that?
Yep, and hit the save button up here at the top. And we'll pull it up.
Save it.
Perfect. There we go. Awesome. So, as is, will this compile?
No, use define it.
Yeah, what do we need to do?
Like int midpoint or something?
Awesome. Yeah, let's do that. Int midpoint equals size. Will this compile?
No.
Let's delete this comment and get it out of the way. What won't compile about this?
We're not doing anything with integer, so we need to print it or something like that.
Yeah, exactly. So we'll get an unused variable. What else is not going to work about this? I think you said something, Sam? Semicolons. Yeah, missing those semicolons. It's going to be a constant thing throughout the course of the term. So the final thing I'll do is I'll put some white space on either side of this operator here, since that's typically how we do it according to our style guide. So we've got the midpoint of our array. So now, if we remember back to our algorithm, what was the second step that we had to do once we have the midpoint?
If it's left, if it's greater, like we'll look at the left.
Yeah.
Something like that.
Yeah, so we have to do some sort of comparison. And what are we comparing here? You said if it is greater than, what is it in that sentence referring to?
The number that comes up, if that's greater than the midpoint, then go to the right.
Exactly. So the number that comes up when we, so the needle,
Yeah.
so we're comparing to the needle. And what are we comparing against the needle? Because the needle is what we're looking for. We're comparing it against the midpoint. But does it make sense to check to see if needle equals midpoint? Does that make sense? Okay. Does anybody disagree? Let's give it a try. If needle equals midpoint,
Print if you found the needle.
printf, we found it. Otherwise, I'm going to start doing something different here. I'm going to start putting braces around if statements all the time, just because if we add more stuff, then we don't get the compile errors. Yeah, Sam, you've got a point.
Yeah, the problem is that midpoint represents a position in the array, but you need it to represent the value in that position of the array.
Ah, that's a great point. Did everybody hear what Sam said? He said that midpoint, as is, represents just a position in the array, but it's not the actual element in the array. So if we think about the code as written right now, if we look at this array down here, which has 8 elements in it, what is the value of midpoint going to be in this function?
4.
4. Okay. So if we look for the number 4, we can just run this code, put a little sad face in here because we didn't find it. So if we run this code as is right now, uploading it, building, let me scroll down, and if we look for the number 4, we found it, but we didn't get this to printf yes. One reason is that, well, we didn't return true, but did we really find the number 4? And Sam is saying no. What did we find? We really found the midpoint, which if we look at the array down here, it's going to be the element at index 4 is that we're looking at, which is 23. So how do we actually get that element at the midpoint, and not just the midpoint itself?
Convert it into a chart or something.
So what would that do, just out of curiosity? Can you elaborate a little more?
You have to transform like the position into the number, right?
Mm-hmm.
So you've got to make some connection. I'm guessing it's a chart, but it might not be.
Yeah, no, so that's a good point. We've been doing a lot of this converting positions into chars, into these characters in the first 2 problem sets. It turns out that here, this is almost similar to accessing the ith character within a string.
If you want to do
Does that make sense? So here we want to access the midpoint element. So how do we do that? Kevin, do you have any suggestions how we might do that?
You could do haystack, open bracket, mid,
Okay.
close bracket.
Can you write that for us? Save it in your, we'll pull that up. We're looking at this line 9, and we're realizing that we don't want to compare the needle to the midpoint, but instead we want to compare the needle to the element at position midpoint within our haystack array.
All right.
Cool. There we go. So yeah, that looks pretty good. If needle equals haystack midpoint, we found it. So now if we run the code, we'll back up a little bit. It compiles, it runs, and now if we look for 4, we didn't find it because now we're actually getting the number 23. We're getting the value 23, and that's what we're comparing to our needle. But that's good. That's a step in the right direction. That's what we're trying to do. We're not trying to compare the needle against positions in the array, but rather against the actual elements in the array. So if we look back again now at the next step in our algorithm, what is the next step? Layla already mentioned it briefly.
Check to see if it's greater than or less than, and then decide which way to move.
Yeah. So how would we do that? Can you put in some, I'll save this revision,
Sure.
and then if you put in some lines, that'll do that?
Yep.
Yeah, Charlotte.
I have a question. Yeah, so shouldn't it be midpoint minus 1 because the first thing is it's 0 index, so if we put 4, that's not actually the character we're looking for?
Yes, and the other problem with that is, that's a great catch, because what is going to end up happening, possibly, if we keep moving and we don't ever adjust initially? We might, I guess what we might end up doing is trying to access the element at the 8th position of the array, which in this case doesn't exist. So we will want to do some sort of accounting for the fact that we have some 0 indexing.
Or sorry, or I meant midpoint minus 1 in the square brackets.
We can do that. So we'll come back to this issue in just a bit. Once we start to get to the actual looping, that's when we'll really see this come into play. For the time being, we can just do this. But you're totally right. That 0 indexing will have an effect that we need to account for. So let's see. How is the greater than, less than?
Yeah, I get how to do the greater than and less than part. I just
Uh-huh.
wasn't sure what to print if you find that it is less than the haystack midpoint or greater than. So
Yeah.
here I can save what I.
Yeah, if you save what you got, and we'll pull it up.
Okay.
There we go.
And I put question marks for
Awesome.
where I didn't know.
That looks great. So here we've got question marks because we still don't know what we're going to quite do yet. So what would we want to do? Oops, we've got some braces all funky on us. We'll correct these braces. There we go. And so what do we want to do according to our algorithm if we don't find the needle? Say in the case that the needle is less than what we're looking at.
You only look at the left half.
Right. So we'll put a comment in here that says, look at left half. And if the needle is greater than the haystack at the midpoint, what do we want to do? Look at the right half. Look at right half. Not too shabby. Okay. So at this point, things are looking pretty good. The problem with the code as written is what?
We don't have endpoints for the halves.
Right. We don't have endpoints for the halves. We also are only going to go through this once. We're only going to look at one midpoint. Either the element's there or it's not. So in order to complete this, we'll need to do some sort of repetition. We need to keep repeating until we find that either the element's in there because we've narrowed down and finally found it, or it's not in there because we've looked through all of the things in the appropriate halves of the array and found that nothing's in there. So whenever we've got this repetition going on, what are we going to use? Some sort of loop. Yes.
Can we do a do while loop and have it do that, and then while the needle does not equal the what? I'm not sure where I was going with that, but kind of like until it does do that as long as it doesn't equal the value that the user inputted.
Yeah. So let's see. How might this write itself? You said let's use a do while loop. So where does the do start?
Right after the size divided by 2.
Okay. And what are we going to do? We'll fill in the while later. What are we going to do?
Don't we want to do all the stuff we have in the if portion?
Do all this stuff. Great. Copy and paste. Oh, man. Let's see if this works. If we can tab this over. Oh, beautiful. Okay. Let me save this so you guys have it. All right. And we are going to do this while. What was the while condition you were after?
While the needle does not equal, so like the exclamation point.
Okay.
But I'm not sure exactly what value that is yet.
Got it. Yeah, so this is one way to do it. Sam, you have a comment?
Yeah, I remembered when I watched the videos, I took a screenshot of one of the, like when they did the pseudocode for it, and they had something, some relationship between max and min. I think it was like something like if max is ever less than min.
Got it.
Or something, or like if max is not less than min or something like that.
Okay.
Because that would mean that you've searched everything.
Yeah. So what does it sound like max and min were referring to?
Values that, integers that are going to change relative to where we put the midpoint.
Exactly.
Because the midpoint is going to be copied of the max, of the new max and the min.
Right. So the midpoint is kind of this max and min idea. Does that make sense to folks? So if we were to start looking at how we're going to do this iteration, totally right that we want to use some sort of do while loop. But if we remember what's going on at the bottom of this array and what's actually happening, I'm going to write over here. At the very first iteration of binary search, we have, I'm going to use B and E to denote the beginning, oops, and then the end of our array, right? So we know that the beginning is at 4, right over here, and we know that the end is at 108. Say we're searching for the number 15. So the first time we do this, like we saw earlier, the midpoint is either going to be 16 or 23, depending on how we calculate things out, since evenly dividing in the middle would give us this space between 16 and 23. We can't evenly divide it, or divide it and get a true midpoint. So we'll look at 16. We'll realize, hey, 16 is greater than the number 15 that we're looking for. So to then look at the left half of the array, what we'll end up doing is discarding this entire upper portion and saying, okay, now our endpoint is going to be here. The next iteration of our loop, we're now just looking at this array, effectively having discarded this portion, because now if we're taking the midpoint to be the difference between the beginning and the end, we find our midpoint to be 8, which we can then test 8 to see where it is in relation to the number we're looking for, 15. Find that 15 is greater, so we have to move to the right portion of the list, which we know because we're humans and we can see it. We know that the right portion is going to be where we find it, but the computer doesn't know that. So what we'll do is we'll actually have this go up, and now the beginning and the end are the same spot. So the midpoint becomes the only number in the list at that point, which is 15, and we found it. Does that shed some light on kind of where this whole max and min notation is going? Keeping track of the endpoints of the array in order to figure out how to narrow things down? Okay. So, what were to happen if this weren't equal to 15 now? What if we were looking for 15 and instead this number were also 16? We'd say, oh, it's greater. We want to go back to the left, and we'd move our e to the right, at which point we'd have an endpoint that would be conflicting. We wouldn't be able to search for any more elements, because now we have our endpoint and our beginning point, our max and our min, are now flipped. We've searched through the entire array. We can't find anything. So that's the point at which we'd want to say, OK, we're going to stop this algorithm. We haven't found anything. We know it's not in here. How is this going?
How exactly does the computer switch the end? How does the end end up before the beginning?
Got it. So the end ends up before the beginning because of the math that we're going to do each time we do this. The way we swap is if you look at the very first time we do this swap, where we have the beginning at 4 and the end all the way down at 108, and our midpoint, say, at 16. If we're looking, I'm going to reset this back to 15. If we're looking for the 15, we knew that what we did when we checked the 16 and saw that it was greater and wanted to discard the entire right portion of the list, we saw that what we wanted to do was move this e right here. Right? So effectively, the e got moved to 1 before the midpoint. Right? Likewise, when we did this iteration of the algorithm and the midpoint was at 8, we found that 8 was less than 15, so we wanted to move the b 1 past the midpoint. So now that the beginning and the end are both together at this 15, if we'd been happening to look for some other value, not 15, or if this 15 had instead been a 16, we would have found that, oh, well, the e, we want to move 1 before the midpoint. So now the e would be there, flipped, less than the b. Okay. So let's walk through how we actually end up coding up this algorithm. We know that we want to have this midpoint calculation. We know also that we want to track the beginning and the end of the array, of our current array, just so that we can figure out where this left half of the list is and where the right half of the list is. So we do that with either begin and end, or we can call them min and max. I'll use begin and end this time. So when we begin, if we look back at our example down here, our beginning was set to the very beginning of the array. That's natural. What index was this? What should our begin be? Danielle.
Haystack, bracket, 0, bracket.
Yeah, so we could set it equal to haystack 0. The problem, though, is that this gives us not the position of the first element, it gives us the index of the first element, or the actual value at that first position.
So that convert the point to 0?
So what this will do is, well, it won't do any converting. What it'll do is it'll just store a 4 in begin. And then it'll be hard to make comparisons against begin. because begin will be holding the value 4, which is the beginning of our array, but we want to track the indices in the array as opposed to the values. So we'll actually just use a 0, like that. For the end of the array, Charlotte brought this up a little earlier. This is where we'll take into account the 0 indexing. Charlotte, what's the end of the array? What is the index of the end?
Size minus 1.
Yeah. And which size should we use? Should we use
Capitalized.
capital size or lowercase size?
Capitalized.
So in this case, we could use capital size. If we wanted this function to be portable and use this function in other programs,
Okay.
we can actually use lowercase size just as fine too. But Charlotte's totally right that we want to have size minus 1. So at this point,
How is it you could use uppercase size?
how is it that we could use uppercase size? So it turns out that these pound defines
Right.
are really, under the hood, a text like find and replace, if that makes sense.
Okay.
So when you compile your code, the pre-processing phase of the compiler goes through the file and it looks for everywhere that you've written capital size. And it replaces that text literally with an 8. Just like that. So in that sense, this is very different from a variable. Like, it doesn't take up any space in memory. It's just a simple text replace trick. In this case, we're going to use size. So from here, we do want to do some sort of repetition. And we're on the right track with our do while loop. We want to do something until a condition doesn't hold anymore. And as we saw earlier, we saw that that condition was indeed that we don't want the end to be less than the begin. This is our stopping condition. If this occurs, we want to stop and declare like, hey, we haven't found anything. So to express this, we do want to use a while, some sort of loop. In this case, would it be a do while loop, a for loop, a while loop? We have a do while loop here. Do you guys like that approach? Do you think we should try a different approach? Kevin, any thoughts?
Well, we could just have a while loop,
Okay.
because if mid isn't, I mean, we know max will be greater than mid at the start anyways.
Mm-hmm. Yeah, so there's no initialization that needs to happen. So those do while loops are great when you have to initialize something before then testing. Whereas here, we know that we're not going to keep reinitializing both begin and end every round of the loop. We know that we want to initialize them, then check our condition. So in this case, I'll actually go with a simple while loop. It turns out that do while loops are used fairly infrequently. A lot of places don't even teach do while loops. They're good for handling user input, so we've seen a lot of them thus far. But normal for and while loops are a lot more common. So it turns out that this condition as written won't really do us much good. And why is that? I'm sorry, I don't know your name. Can you?
Oh, I'm Jerry.
You're sorry?
Borut is B-U-R-U-I.
Oh, B-R-E-I. Okay, cool. I don't see you in my list. Oh,
I think this is
that's because it's oh, that makes sense. So why do you have an idea of why this while loop might not work as intended, as written with the condition?
You mean like you want to put all the stuff behind after it into the bracket?
Yeah, so that's one. But more, so we might have to put all of this stuff into the while loop, which is totally true. The other thing that's a little more problematic, though, is that this condition doesn't work.
You need to flip it.
Right. So this condition just won't ever be true initially. The way we talked about it, we want to do something until end is less than begin, but we want to do something while begin is less than or equal to the end. So there's kind of that reversal of the logic there. I'm guilty of making those mistakes all the time.
Why does it have to be less than or equal to?
Because do you remember the case that we got to where there was only one element and we were down and we were looking at just the 15 in our array? Our beginning and our end were the same element. We want to make sure that we handle that case. If we just did a straight less than, we would only be able to get down to a 2-element array. Once we got down to that last element, if that were our element, we'd never find it. All right. So now, here we can do exactly just like you were saying. We can start plopping stuff right into the middle of our while loop. We can plop in our midpoint. We can take all of these if statements, pull them out of this do while loop, plop them in, clean things up a little bit, and I'll go ahead and save this revision. And now at this point, we're getting pretty close. Okay.
I think you also have to have int midpoint equals size minus 1 over 2.
Got it. Size minus 1 over 2. Is there anything else we need to change about that line? That was a good catch. What does size do? Are we ever changing size? In order to keep the line like this, we'd have to change the size. We'd have to change the size every time we go around the for loop. But remember when we were going through our example just a little bit earlier, and we had the beginning at 4, and the end all the way over at 108. How did we calculate the midpoint? Were we using the size? We were using begin and end instead.
It's the difference between the end and beginning.
Exactly. And how exactly should I write that, Charlotte?
So just end minus begin.
Okay.
You wouldn't need to do the minus 1 because the minus 1 has been included in the end and the begin already.
Great. So you're totally right. We don't have to do the minus 1 because that minus 1 has been included and taken and accounted for when we initialize the end variable. Is there anything I need to do else syntactically to have this line make sense?
Plus begin.
Plus begin?
At the end. Because
Plus begin.
it's only calculated half the length difference, but you need to add the begin like 2.
So what would this calculate for us? So if we think about end on this very first iteration of the loop, end is going to be in position index 7. Begin is in position 0. Remember, we're looking for either position 3 or position 4. So if we look at this math, just to make it a little more tangible, we'll put some numbers here. We know 7, 0. So 7 minus 0, and then divided by 2 is 3. In integer division, that is. So then, do we need to then add back our begin? We don't in this case. On the very first iteration, it'll be fine because begin is 0. But as we progress, we do really all just need end minus begin divided by 2. So there's one other trick here, and that is namely one of precedence.
Do we need parentheses?
Exactly. Exactly. And that's because if we don't put these parentheses, then this line will be interpreted instead as end minus begin over 2, which we definitely don't want. So watch out for those precedence rules.
What about, why wasn't it end plus begin?
Why is an end plus begin?
Why is it not that?
Why would it be plus? I think you're right.
Because it's average?
Mm-hmm. So end plus begin. You're totally right. Wow. I just totally goofed. You're totally right. If we were doing the minus, we would want to add the begin back in. In this case, you're very right that we want to take the average of the two. So we do want to add them as opposed to subtract them.
It would also work if you did end minus begin divided by 2 plus begin.
It would if we do, I believe so. So if we've got, for example, if we were looking at begin and we shifted it over here to the 15. So now begin is at position 2, end is at position 7. If we divide by, if we subtract them, we get 5. Divide that by 2, we get 2. And then we add 2 back in, and that gets us to the 4th position, which is right here, which is the midpoint.
Do we need to take care of rounding?
In what sense do we need to take care of rounding?
If the sum or the difference between, depending on how we do it, is not an even number, so then the computer gets confused whether it's like, when it's 2.5, do you move to the left or to the right to determine which is the midpoint?
Got it. So it turns out that with integer division, we don't ever get these floating point numbers. We never get the decimal. It's just totally discarded. So if you have a computer divide 2 int variables, and one is 7 and the other is 2, you won't get 3.5 as a result. You'll just get 3. The remainder will be discarded. So it's effectively rounding, not a round, but rather a floor, if you guys are familiar with that in math, where you just completely discard the decimal. And so you're essentially truncating it down to the nearest whole position, to the nearest whole number.
But then that's problematic because if you have an array of 7 elements, then that automatically picks the 3rd element as the midpoint instead of the 4th. So how do we deal with that?
So it's problematic because if we had an array of 7, it would pick the 3rd instead of the 4th. So why is that? Could you explain a little more?
Because if you have 7 elements, then the 4th element would be the middle point, right? Would be the midpoint.
Remember your comment about being 0 indexed, though.
Yeah. So in position 3, that would be the midpoint.
Yeah.
But if you, okay, I see what you mean.
Yeah. So it's kind of a weird, as we get used to this whole notion of getting rid of decimals. That's a great point. Okay. So let's finish this up. So we've calculated our midpoint. We're testing to see if our needle is equal to the middle value. We're printing that we found it. But really, what do we want to do in this situation? We found it, so we want to let the caller know that we found it. We've got a function that's a Boolean typed function. So the way we signal to the caller of our function that we're ready to go is we say, hey, we have, this is true. So how would we do that, Kevin? You're nodding your head.
Return true.
Yeah, exactly. Return true. Now, if it's not equal, how would we look at the left half? Any ideas? Stella, any ideas?
You need to set a new position for end.
Yeah.
So we have to do position of midpoint minus 1, something like that.
Great. So we need to set a new position for the end to look at the left half. This was what we talked about before, where I keep going back to this example. I had the begin here, and then I had the end all the way over here. Again, if we're looking for 15 and our midpoint is at 16, and we realize, oops, 16 is greater, we want to move to the left half, we would then move the end to the 15. And we do that by taking 1 away from the midpoint and setting that as our new end. Likewise, if we want to look at the right half, how would we do that? You have an idea?
You just set beginning to midpoint +1.
Great. And now in the case that we don't find anything, does that get taken care of for us? Daniel, does that get taken care of for us?
No.
If we make it through the entire array and we don't find anything, where would that be taken care of?
Oh,
Or where
the
should we
while-
take care of
the
it?
while condition?
Yeah. So the while condition. Exactly. We'll take care of going through the entire array. If we don't find anything, this while loop will end. We will never have encountered this condition, and we can just return false. So we can also leave this if in here like this, because if this if statement is true, then our function will return. And so we'll just essentially abort this function at this point when we return true. But what happens with this structure here? Will this work entirely? Or is there some logical flaw in there? There is some logical flaw in there. That's the way I'd say it. What might it be?
Why do you need the minus and plus ones?
That sets our array up to be our new left half and right half.
Well, why couldn't you just do it without the minus ones and plus ones?
We could just set it equal to the midpoint.
Yeah.
What might be problematic about that?
I guess it's inefficient because you're checking a value that's already been checked.
Exactly. So Sam's totally right. If you set the end and the begin equal to the midpoint instead of -1 and +1 respectively, at some point in the future, we'll end up checking the midpoint again.
And just, I started the P set and I
Mhm.
had something like that where I forgot the +1 and got stuck in an infinite loop.
Right. Because at some point, you're never going to get begin and end to actually overlap. Cool. So there's one more logical flaw, and that is that this should definitely be an else if. Why might that be? The reason is if it's not an else if, did you see it, Kevin?
Yeah, because you're changing the endpoint.
Exactly.
Or, yeah.
Exactly. We're changing the endpoint. And if it's written like this, we'll make spaces between, then it'll check this case. This case, if it succeeds, will just abort out of the function. Then it will check this next case, and if this succeeds, it'll adjust the endpoint. And then it will continue on and check this case. But at this point, we don't want it to continue checking. Fortunately, we haven't reset the midpoint here. And we know that this case won't succeed. But we definitely want to put the else if in there, even though that might. In this case, since we're not adjusting the midpoint, would that make a difference? No, because these cases are all exclusive. So maybe, again, my bad. I don't think need this else if. We can give it a try and run it and see what happens. Building, an error occurred. It's probably because I left these B's and E's in here. Do I have any more of those up at the top? Doesn't look like it. Let me zoom out, build. There it goes. So now if we search for 15, yes. Zoom in, 15, yes. We can run it again. Uploading source code, building, running. We can search for something like 13, and we don't get anything printing out. So it's not finding that for us. But that's great, because it's not in our list. So we are now out of time. That's going to be it for this week. Thanks for joining, and See you later.